you for joining us today. Today, my colleague Wyatt and I are going to talk about high-performance computing on Google Cloud. My name is Emma. I'm a developer advocate for Google Cloud Platform. Okay. So we have 4 chapters today. The first part is we'd like about reviewing what HPC is and what it means on cloud. And then we'd like to talk about some of the cloud offerings we have for HPC applications. Then Wyatt will be discussing job management on cloud and some of the real-world case studies. So let's take a close look at what HPC is and what it means on cloud. High-performance computing, or HPC, is generally characterized as massively parallel and with a lot of data. So massive parallel means a lot of cores from tens of thousands of cores and sometimes hundreds of thousands of cores. And a lot of data usually means petabytes, sometimes exabytes of data. HPC is one of the most important areas in computer science. It powers a lot of different industries, such as scientific simulations, engineering, financial services, health and life science, data analysis, and more. So these are just a few examples. But when you think of high-performance computing, there are actually 2 slightly different types of workloads. The first kind, or the first type, is high throughput, or what we call embarrassingly parallel computing. So these types of workloads are relatively independently working on each of the nodes. So they communicate less often between nodes. The example types of workloads include financial services, genomics, media transcoding, rendering, and data analysis. So these types of workloads just works fine on cloud today, and there are a lot of examples. The other type of workload is tightly coupled or just parallel computing. This is more of the traditional area in high-performance computing. Applications might use MPI as a programming interface. They often communicate between nodes. So they require low latency, high bandwidth network. And of course, they also require a lot of storage, and they must be fast enough. So this is more about scientific engineering and computation. Example use cases are like computational fluid dynamics, electronics, engineering, and product design, oil and gas research with physics and chemistry. And we actually have a lot of real use cases and customers running these 2 types of workloads, including the high throughput computing and tightly coupled computing. So, while we showcasing some of the examples during this talk. HPC requires a quite different kind of infrastructure when compared to web applications or mobile backends. Of course, it requires a strong computation power and a lot of storage. And as they communicate between nodes, they require low latency and high bandwidth network. And as we will need to manage a lot of nodes, we need some sort of software to manage these HPC deployments. And of course, we need to be cost-friendly. Why would we need to use cloud or migrate to cloud? Well, in the world of on-premise HPC clusters, we usually have relatively smaller number of configurations. For example, we might have a single configuration of nodes with CPUs and GPUs and the same amount of memory for all of the nodes. So they usually have one or a few queues. So all of the users have to use the same configuration, same queue. sometimes these machines are too big or too small for these workloads, so there are some computational resources that are left unused. But with cloud, you can configure as many clusters or as many queues as you need. And on top of that, you can resize these virtual machines as necessary and add SSDs or GPUs as necessary. For example, if some of your users need just CPUs, we can set up a cluster with CPUs. And if another user might need GPUs, we can add GPUs just for the user. So these are more resource efficient and cost efficient. And of course, these clusters can be scaled in and out as necessary. And we can go even further. For example, when your task needs exactly 20 CPUs and 46 gigabytes of memory, we can provision virtual machines of the exact size. We call it custom machine types. We'll explain later. But this is the idea of having virtual machines and computation nodes on cloud. So let me introduce some of the cloud offerings we have for HPC applications. Computer engine. So computer engine is one of the most fundamental components on Google Cloud. They are high-performance virtual machines with access to the latest generations of hardware, including Intel's Skylake processors and NVIDIA Altair GPUs. They are very easy to provision. They can be started within 10 seconds or 20 seconds. So when you are starting hundreds of nodes, they will be ready within a minute. And we have the web interface, command line utility, and web API. So you can start using the cloud with the web interface. And when you need to automate certain tasks, you can migrate to other methods to control your cluster. Of course, we take security very, very seriously. We have more than 750 engineers and security experts working to protect our infrastructure. They're not only working on the software we run on our platform, but also the hardware, network, and physical infrastructure. So they're designing and engineering all aspects of our platform. And we use the same network. We have one of the strongest networks for public cloud providers. We use the same network for Google Cloud that we use for our services like YouTube, Search, Maps, and all the other applications. So running your application on Google Cloud means you will be benefited from the network and infrastructure that we use to run our services. These are some of the numbers and details. So computer engine is very flexible from 1 core to 160 cores, and you can scale up to nearly 4 terabytes of memory. And you can, of course, attach GPUs and SSDs as necessary. And you can configure preemptible VMs and GPUs. These are mechanisms to save costs. I'll explain this part more in detail later. Since this is very flexible, you can install any operating systems or any software that you need to run your software. So computer engine can be used for MP applications, batch HTC applications, real-time processing, MapReduce, and machine learning workloads. So this is very flexible. Having access to the latest generation of hardware is even more important with cloud. With Intel Skylake CPUs, your application might run faster by up to 82% with access to the AVX512 instructions. Shorter runtime means not only you get your results faster, but also you can terminate these instances earlier. So you don't have to pay for the idling time and wasted computing resources. We have GPUs as well. You can touch up to 8 GPUs per virtual machine. They're directly attached to these virtual machines via PCI Express, so they are close to the bare metal performance. And GPUs also support preemptible virtual machines. We offer NVIDIA Tesla K80 P100 and the latest Volta V100. We have a couple of block storage options. The first option is the local SSD. They are directly attached to the virtual machines. They are ephemeral, so when virtual machines are terminated, the data on this storage will be lost. But it is very fast, with 680 kilo IOPS for read and 2.5 gigabits per second of throughput. You can add up to 3 terabytes of SSDs to a single instance. This is best to be used for temporary data and frequently accessed cache space. We also have persistent disks with SSDs and HDDs. So as the name implies, these are persistent. So even when virtual machines are terminated, the data will be kept. With SSD, SSDs are best for latency-sensitive applications and data. They have up to 40K read IOPS and 800 megabytes per read of throughput. Hard disks are very cost-effective. It is best suited for latency-insensitive tasks and lots of data. Both of these persistent disks can be scaled up to 64 terabytes per instance. And we offer other features, such as snapshots, encryptions, and others to protect your data. We also offer object storage, cloud storage, for large unstructured data. These can scale up to exabytes and can be accessed from any of the virtual machines and even from outside of Google Cloud Platform with the REST interface. The latency with the object storage is higher than persistent disks, so they are more suited for bulk kind of operations. We offer POSIX-compliant storage with GCS Fuse, so you can you can mount these storage buckets from your Linux instances. We have some of the best networks. You can launch up to 7,000 virtual machines in a single network. And they have relatively predictable low latency between nodes with 40 to 60 microseconds. The bandwidth depends on the number of cores, but they can scale up to 16 gigabits per second. So this is faster than 10 gigabit Ethernet. And in order to achieve this performance, we design our data center network from scratch. We use closed topology network so that these nodes can communicate to other nodes relatively regardless of their physical positions. Not only the intra-data center network, we also have a global Google network. So you'll be seeing this big diagram before, I think, but these blue lines are existing cables that Google uses, and these green lines are new optic fiber cables that we invest in and build with our partners. So when you are working with other institutions and working on international projects, you can move your data from one continent to another. We offer options to save cost. Custom machine types, I talked about this briefly before. This is a mechanism to pick any configuration that matches your workloads. This is as easy as moving these slides on the web interface. You can choose from 1 core to 106 cores very easily by moving these slides, and the same for the memory. Our customers have saved on an average of 90% or up to 50% by using custom machine types. So this is about choosing the right size of virtual machines for your workloads. These numbers are from the real customer examples. And we also offer preemptive virtual machine instances. They are discounted by up to 80%. So they are super low-cost, short-term instances. So they might get preemptive. So they have the maximum lifetime of 24 hours. They might run up to 24 hours, but they are not guaranteed to be alive for 24 hours. We might have to terminate them, but they are discounted in return. And we have reduced pricing for attached resources such as local SSDs and GPUs. So if you run preemptive VMs, your attached resources are also discounted. And even with preemptive VMs, you have access to the same set of hardware that we offer for regular VMs. So this is best suited for relatively shorter lifetime tasks and high throughput computing or high independent jobs kind of tasks. They can either be started again from scratch or can be resumed from checkpoints. So even if you have to run the same task again, they are discounted further. So in total, you can save cost. Now, I'd like to welcome Wyatt to talk about job management and real use cases on cloud.
Hi, everybody. Thank you, Emma. So Emma's just given us a great overview of the infrastructure that we could use to build high-performance computing clouds. So I want to talk now about how we can run and manage jobs on those high-performance computing clusters in the cloud, what software we can use. I want to give you all a couple of opportunities to get your hands dirty. So if you want to take your laptops out, I have a couple of links that you can load up some code labs and tutorials. And then I want to talk about some real-world customer use cases where we've seen our customers running their high-performance computing applications in the cloud. So we have a number of workload management partners. So first of all, what is a workload manager in high-performance computing? In traditional high-performance computing, a workload manager, their job is pretty much limited to managing resources and allocating jobs throughout a cluster, right? So that means that you build your cluster, you configure it with your operating system and everything like that, and then you install a workload manager on top of that. And then you use that workload manager to submit jobs, and that workload manager allocates those jobs throughout the cluster to manage those resources and best bin pack, it's called, right? So in the cloud, the role of a workload manager expands a little bit often. And so they often take on the responsibility of building the cluster, provisioning the nodes, configuring the nodes even, and everything like that. Those are the sorts of things that you can't do with hardware, right, in software. So they even extend often to scheduling maintenance tasks and tearing down nodes as needed. So we have a number of partners, as I said. I want to just focus on 3 of them today. So the 3 we have today are Altair's PBS Cloud I/O. This is a really easy-to-use, web-based management system. We have SCEDMD's Slurm, and we also have HTCondor. So for the people who are here, who's used these pieces of software somewhere on-premise already? Just a few people. Great. This is an intro course, so you're all in the right place. Who's used it on the cloud, though? Any of these pieces of software? A couple of hands went up that didn't go up earlier. That's great. Warms my heart. So I'm hoping to get everybody's hands up by the end of this because we have a couple of tutorials and code labs we can do. So first of all is Altair's PBS Cloud. For anybody who isn't familiar with Altair, they're a company that develops software for things like computational fluid dynamics, structural simulations for engineering, crash simulations in automotive and military uses. So they have this suite of software, and they really wanted to build a system that would allow their customers to run these jobs very easily using the cloud resources, right? So what they built was pbscloud.io, and they built it on GCP. So PBS Cloud I/O, like I said, is a very simple to use web-based GUI where you can log in. When you log in, you provide a Google Cloud Platform billing ID. So that's the only tieback you really have to Google Cloud to know that you're running on Google Cloud. So you provide this billing ID, and then you get a menu of possible solvers, Altair software, and others. And you can provide your input data. You can provide the way you want the job to scale, any limits or anything like that you want to apply, and click launch. And it'll go and spin up the nodes. It'll show you that it's spinning them up, configuring them, and then actually allocating your job across those nodes, tear the whole thing down once it's done, and provide your output data into a Google Cloud Storage bucket, for example. Right, so this is a really, really easy way to get started with some workloads that you already have that are independent, right? So you can go and log on to pbscloud.io today, provide your billing ID, and start launching jobs, right? So that's a very simple way to get going. That's not typical in HPC, though. So Slurm is another more traditional HPC workload manager. It's very popular. It's open source. It's used in some of the largest high-performance computing clusters in the world. And so we partnered with SkedMD, who are the developers and maintainers of Slurm, to bring Google Cloud native functionality and integrations into the Slurm workload manager. And so we announced this at Supercomputing 2017. These integrations are available on Slurm's GitHub. So if you wanted to Google them right now, you could go and look at all the code. And so there are 3 ways to use these integrations. The first is a standalone auto-scaling cluster in the cloud. The second is a burst-to-cloud use case where you have an existing controller, an existing Slurm cluster, and you can actually spin up just independent VMs in a cloud project and run jobs on them as needed. And the third is a Federate to cloud use case that's really popular, and I'll talk about the cloud auto-scaling and Federate to cloud a little bit more. But for anybody who wants to get started, this is the link right there. You can load that up. That's a code lab, a Google Code Lab, that'll guide you through setting up a project, downloading the Slurm integrations, and configuring them and launching a cluster, and then even scaling it to meet demand. Or you could search Google Slurm Code Lab. Everybody got that? Got your pictures? Great. So it's just down here at the bottom if anybody needs it as well. So in a cloud auto-scaling implementation, it's, like I said, a standalone cluster in the cloud. So what does that mean? It means you have a login node, as is traditional in any HPC cluster. You want an independent login node that isn't actually doing any work, so that if it goes down when you're SSH'd into it for some reason, nothing's affected. So you have a login node, a controller node. That's the node that's actually running the Slurm controller, the Slurm database, the Slurm accounting daemon, and everything like that everything reports back into to get its job allocation. And then you have the compute nodes, right? So all of these are running on Google Compute Engine. And so the cluster auto-scales according to 2 parameters. It scales up and down. So the parameters are first job requirements. So if any one job is submitted that needs more resources than the cluster currently has, it'll spin up resources to accommodate that. So for example, if you had a cluster of 2 nodes, 2 compute nodes, for example, and you submitted a single job that required 4 nodes, it'll spin up those 2 additional nodes, integrate them into the cluster, and allocate the job to those 4 nodes, right? The second is queue depth. So this isn't something that a lot of people think about very often, but if you were to submit, say, 4 single node jobs, right, each job only requiring at most 1 node, then a workload manager might just allocate them all to the same node. Depending on your oversubscription settings in Slurm, though, you can scale to meet that. So those 4 jobs would spin up an additional 2 nodes to meet the 4 nodes that were required by each of those 4 jobs, right? So very dynamic scaling to meet requirements. And then, like I said, it spins them down as well afterwards. So according to an adjustable idle timeout, the nodes will be deprovisioned and deleted in Google Cloud after the nodes are idle, so that you're not paying for any unneeded, unnecessary usage or compute time. The best part of all of this is that once you deploy the Slurm cluster in the cloud, for anybody who's used Slurm before, it's the same tools that you used before. It's the same tools that your users and admins are used to. So it's really easy to get started. The second use case is the Federate to cloud use case. This is where we see a lot of customers going for their burst to cloud needs. So in a Slurm federation, you're able to add multiple clusters into what's called a federation and distribute jobs amongst them, right? So you combine all of these clusters. You actually use a single accounting master server for all of the Slurm accounting, which makes things like Slurm, account management, as well as job placement policies and things like that, which are very powerful in Slurm. Makes it really easy to manage all of those from a single master server. And then you can actually manually assign jobs to independent clusters. If, for example, you knew one user which was supposed to run on just one cluster, you could mandate that they only run on that cluster, or you can allow the federation to allocate that job. And how that works is that the federation actually submits the job to all the clusters, right? So all the clusters get a view of this job, and whichever cluster responds that it can allocate the job the fastest is given that job, and all of the other clusters delete that job replica, right? So a great way to distribute jobs automatically according to whatever is able to respond quickest. So this is really great, like I said, for burst to cloud use cases. A lot of customers have already started doing that. And it's really easy to get started. It's literally one line in your Slurm configuration. You restart the daemons, and you're up and running. So it's really easy to get started. There will be a code lab on Federation that's linked from the auto-scaling code lab as well very shortly. Another example is HTCondor. So this is a really popular workload manager that's specifically designed for high throughput computing, the kind of high throughput computing that Emma introduced earlier. And so it's really easily deployed on Google Cloud Platform using our deployment manager. So we have a tutorial there at that link. You can also just Google search Google HTCondor tutorial, and it'll walk you through the whole process of downloading the deployment manager scripts, installing them, and launching an HTCondor cluster, as well as running a job on them. So now I'd like to go into some case studies. So to show you the power of HTCondor in the cloud, we actually have a great case study. So Fermilab is a national laboratory that does research into high energy particle physics, for anybody who's not familiar with them. They're based in near Chicago. And so they do a lot of work with groups like CERN and other particle physics and particle accelerator groups. And so what they did was at Supercomputing 2016, during the week of the show, on the show floor, in fact, they burst their resources by double using Google Cloud Platform. So in order to accommodate as you can imagine, massive amounts of computing that they do, they built something called HEPCloud, HEPCloud, High Energy Physics Cloud. And so this cloud is really a portal designed to coalesce a lot of disparate computing resources. So they borrow computing time from Exceed and NCSA and a lot of large supercomputing centers and put it all together in this HEPCloud to run their jobs since they're so large. And they decided to use GCP to burst. So they actually burst in a very traditional bursty workload, a 9 to 5 pattern, right, where they see their researchers coming in and doing their work. And they doubled their compute resources from 160,000 cores to 320,000 cores during that 9 to 5 all week. And they were able to do this really cost effectively for only about $1,400 an hour because of the preemptible VMs and custom machine types that we have available on Google Cloud. So if you'd like to learn a little bit more about this and see architecture diagrams and everything like that where they describe how they did this, then there's a great talk from last year's Next called Large Scale and Batch Computing on Google Compute Engine. It's really interesting to have a Fermilab engineer there to present. Just to give you an idea, this is the project they did. It's called the CMS detector. It's basically a 14,000 ton, 1 million pixel digital camera, and it captures about 40 million images a second. So you can imagine the amount of data that generates and the amount of processing that takes. Another great example is our friends Andrew Sutherland at MIT. He's a mathematics professor and researcher. And so he was exploring the generalization of hyperelliptic curves. It's a math problem. And so he needed a really large amount of compute resources to do this work. And so MIT, being MIT, they have some HPC resources, so he went to them, and he said, I need a lot of nodes, a lot of cores to do this job, and I need some very specific software. And they weren't able to accommodate him, so he needed to go to Google Cloud. And at first, as you can see in the blog post on the bottom, he spun up 220,000 cores for a single job. He likes to break his own records, though, I guess. So the next job he ran, he hit 580,000 cores in a single job using preemptible VMs. And he did this on 32 core instances, 18,000 of them or so. That came to about 300 core years of compute. And he did this using preemptible VMs, so he set up checkpointing on the local disks so that when the node was preempted, when a node is preempted, it's just stopped. So you can restart the node, and if it's checkpointed to disk, you resume from the checkpoint, and off you go, right? So very efficient way to do that computation. He said it changes your whole outlook on research when you can ask a question and get an answer in hours rather than months or weeks, right? You start to really ask different questions, and that's really true. The reason he did that 580,000 core job is because he decided to expand his problem space tremendously, to not look at just the traditional curves, but to look at any curves. And he got some interesting results out of that. So you can read more about that in the blog post at the bottom. So what does 300 years, core years rather, of compute time look like in a few hours? Well, there you have it. And the best part of this is that he actually launched this on a Sunday afternoon sitting on his back porch, and it cost less than the amount of money he expected it to cost and got in his grant. Schlumberger is another great example. Schlumberger, for anybody who's not familiar with them, is an oil and gas exploration company. And so they migrated their compute resources to Google Cloud to meet their massive demand. So what Schlumberger does is really sends out ships into the ocean with massive trawler signal arrays and data capture arrays, and they use all of that data to create visualizations of the sea's subsurface to find these oil deposits and tell other people where to drill. And so by using their custom machine types and NVIDIA GPUs, they were able to hit about 35 petaflops of compute power and 10 petabytes of storage in Google Cloud Platform. There's a great talk as well from Next 17 called Supercharge Your Performance Using GPUs in the Cloud. And during that, Ashok Balani, the Executive Vice President of Technology at Schlumberger, said they're leveraging the strengths offered by cloud computation to bring their data processing to the next level. And finally, we have Silicon Therapeutics. They're a drug discovery company based in Cambridge, Massachusetts. And so they shifted their compute to run on GCP. And they, by doing so, were able to find many more active compounds than they were able to previously. So in the blog post at the bottom of the slide there, they said the biggest benefit of using GCP was being able to more thoroughly screen compounds than they ever could have before with their in-house resources, and that it allowed them, the massive amount of compute resources available in the cloud allowed them to find more active compounds than they ever would have been able to find previously, which means that they could probably find more active drugs. So they hit about 16,000 cores and 3 million core hours for only $30,000. Again, this is because of preemptible VMs and custom machine types. They actually used a mix of standard and preemptible VMs, which is very popular. So the standard VMs were used for the longer running and static portions of their jobs. Some of those were coordinating jobs where they would launch sub-jobs or minor jobs and then coalesce all of the results back and launch more jobs again off of that. And then use preemptible VMs for the shorter independent jobs. So they chose Google Cloud because of our Skylake processors, our fast local SSDs, our commitment to open source, and of course that crazy pricing. So I'd like to offer you guys the chance to look up some of these blog posts and a few more that I didn't mention on things like satellite image processing and genomics. And we also have some great talks this week at Next 18. The top one actually happened already, but all of our sessions will be recorded and available on YouTube very quickly. Actually, yesterday's sessions are available today. But we do have 2 more coming up. So research workloads on preemptible VMs is about doing computing on preemptible VMs, really taking advantage of them. And that's with one of our product managers and a couple of people from 2 Sigma, a financial services customer. as well as computing with power not previously possible with BigQuery and Compute Engine. This is actually touching on Slurm specifically. So SUNY Downstate Medical Center and University of South Carolina are using Slurm auto-scaling clusters in the cloud to run their neuroscience research and genomics research, respectively. And they'll be talking on a panel tomorrow. So that's all I had. Does anybody have any questions? If not, please dig into those code labs and tutorials and have fun.